So welcome everyone to the second day and second quantum session of ITCS. So the way we're going to do it is all the questions will be reserved till the end for the panel discussion. So if you have a question, try to remember it, write it down. You can put it in the chat if you want. And I will give a verbal 1-minute reminder to the speakers. So the talk time is 8 minutes, and we'll try to stay on schedule. So with that said, I think the first talk is by Lior Eldar, who will be telling us about robust quantum entanglement at nearly room temperature.
Okay. Okay. So thanks, Anand. Thanks for coming to the talk. Yeah. So this is the subject of the talk: robust quantum entanglement at room temperature. Okay. So let's recall Schrödinger's cat. Right. So we've all heard about this near-death experience. For thought experiment feline, so you have this cat entangled to a poison vial. So if the poison vial is intact, the cat lives. If the poison vial breaks, the cat is not so fortunate. So this is a textbook example on how to explain entanglement. But actually, it's kind of a cynical view of entanglement, right? This is kind of Schrödinger's way of telling us that we're likely to see large-scale macroscopic entanglement as much as we can kind of see this creature entangled to a poison vial. The question is this cynicism justified in any way? So when in doubt, we blame decoherence. Right? So let's recall what decoherence is. So we start with a nice, clean, pure state. You couple it to a heat bath, which is an auxiliary system to which we have no access to when you let it thermalize, and that would reach some form of equilibrium. So decoherence or uncontrolled thermalization is usually cited as the root cause we're still not selling quantum computers by the dozen, or that we can kind of see Schrödinger's cat in real life. So when we compare theory to real life, so ideally we'd like to manipulate pure states on many qubits, but in reality, we're unable to retain purity as the number of qubits grows and temperature increases. We only get mixed states. So physically, in fact, when you think about it, there is actually just one mixed state. It's a thermal state. It looks like this. It's e to the minus beta h over z, where beta is the inverse temperature. It's 1 over the kappa t, where kappa is the Boltzmann constant, and h is some Hamiltonian. It could be a local Hamiltonian, and z is the partition function, all of the exponents of the eigenvalues. So coming back to the question of entanglement at room temperature, there is a kind of an underlying quantum mechanical question whether entanglement is inherently fragile. In other words, could it be the case that we're not supposed to see entanglement at room temperature? In other words, it dissipates into this probabilistic mixture as the number of qubits grow. Now, so now the challenge would be then to stabilize entanglement at room temperature at macroscopic scale. And the technical challenge would be to design a preferably local Hamiltonian H for which e to the minus beta h is entangled. Okay. So we use a necessary condition for entanglement, a property, which is quantum circuit low bound. So let's just recall for a second what is a quantum circuit. It's something that looks like this. So you have a product of these d unitaries, where each one is a tensor product of these two local gates. And you have d of those. So this is a depth d unitary circuit. And now we can talk about circuit complexity. So given a mixed state rho, the circuit complexity of rho is the minimal integer d for which there exists a u of depth d, such as if you apply to the O of 0, which is unentangled, completely unentangled, and maybe trace out some subsystem of the qubit, you approach your target state rho to some vanishing error. Okay, so this is circuit complexity. And now you can talk about the following conjecture. It's called robust topological order at room temperature, which posits the existence of a local Hamiltonian H on n qubits that is both topologically ordered, in other words, it's uniquely quantum at the ground state. And for beta, which is O of 1, the thermal state has high circuit complexity as follows. In other words, the circuit complexity of the thermal state at constant temperature diverges fast enough for you to potentially able to couple any pair of qubits in your system. So truth be told, right, we know of many local Hamiltonians with high entanglement at the ground state. For example, any quantum error correcting code with large systems. But we don't know of any such Hamiltonian for which the thermal state at high temperatures retains a circuit low bound. In other words, for all we know, thermal states of quantum error correcting code could be simulatable by shallow circuits, classical distribution. So the main theorem that we show here is, in fact, the conjecture holds for nearly optimal parameters. In other words, there exists a local Hamiltonian edge on n qubits that is simultaneously topologically ordered, in other words, it's highly entangled at the ground state. And for beta, which is maybe not a constant, but O of log log n, in other words, the temperature is just almost constant, 1 over log log n, the thermal state has the desired circuit complexity, and it's lower bounded by omega log n. Okay. So in fact, we show that more is true. In fact, we show that the thermal state of these Hamiltonians is locally decodable to a highly entangled state. In other words, the circuit lowbound that we cite here is not just an indication of these long-range correlations, but in fact, indication of quantum long-range correlations. So in fact, this establishes that it could be the case. It's an indication that thermal states could be holding a high degree of entanglement in macroscopic scale. So let's just give an overview of the technique because we don't have a lot of time. So we first use quantum locally testable codes. And quantum locally testable codes are something that translates energies to errors. And then we consider the thermal state and show that for high energies, you get high fraction of errors, and for low energies, you get low fraction of errors. And then we use another thing, which is to say, well, now we have this unique state, which is the thermal state. Let's see what it means on these states. We show that if we analyze the thermal state as a random error model, and you let the error model evolve under a Hamiltonian, which is a quantum locally testable code, then something else exists. Not only do you get low-weight errors can form large clusters, but specifically for the thermal state, the low errors become very, very sparse. And this is important because in this regime, and not in this regime, you get another property, which is shallow decoding. You can actually apply a form of the Fisher-Spielmann decoder to get from your thermal state to a quantum error correcting code state, which is highly entangled. And this allows you to conclude that the thermal state itself is highly entangled. So as a take-home message, I would say we can't yet stumble into a cap poison entangled state, but if you allow your Hamiltonians to be local but not spatially local, but kind of Barak mathematical construction, then you can get quantum systems that are, on one hand, truly quantum at zero temperature. They're topologically ordered, and yet their entanglement seems to persist at very high temperatures, nearly constant temperatures, but decay only very gradually with systems die. That's it.
Okay, so thanks, Lior, for a great talk. Yes, I guess we'll move on to William's talk now.
Let me just share my screen.
Yeah.
Sorry, can I get started?
Yeah, I think so. So I'll just introduce you. So the next talk is by William Kretschmer on the quantum supremacy, Tsirelson inequality.
All right. Thanks, Anand. So recently, as in just a little over a year ago, a team at Google announced the first experimental demonstration of quantum computational supremacy. And they did it for a problem known as random circuit sampling. So they would sample a random quantum circuit C here with like 1 and 2 qubit gates. And they tried to sample from its output distribution. And the benchmark they used to verify their experiment was something known as the linear cross-entropy heavy output generation task, sometimes abbreviated XHOG. And basically what it says is their goal is to produce n-bit string Z such that the probability of seeing Z under like the ideal output distribution, so that's what this quantity is, such that this quantity is large. And also just a little over a year ago, Aronson and Gunn proved what is essentially like a computational analog of the Bell inequality. Because what they showed is that under a plausible complexity theoretic conjecture, it is hard for a classical algorithm, a polynomial time efficient classical algorithm, to do substantially better than random guessing on this benchmark. Because this 1 over 2 to the n is what you get if you just sample Z uniformly at random, because there's 2 to the n strings, and there's some probability distribution induced on them by this these probabilities. And so this says that a classical algorithm can't do much better than just random guessing. And so when Google was able to announce that they could produce samples that satisfied roughly a benchmark of roughly 1.002 over 2 to the n, so just slightly larger than this, this is basically enough for them to claim quantum advantage for n equals 53 qubits. But this raises a very natural question. If you know of the Tsirelson inequality in quantum information, we should sort of ask, what's the corresponding upper bound here for quantum algorithms? So this is, the best classical upper bound for efficient classical algorithms. So what's the best that a fault-tolerant quantum computer could do on this problem? And it's worth noting that if you assume like a perfect fault-tolerant computer that allows you to sample exactly from C, that achieves something like 2 over 2 to the n on average. But what B is, should this be? And that's sort of the main question we study in this work. And our main result basically says, well, we study this problem in essentially the simplest model, simplest non-trivial model in which you can say anything interesting about this question, which is in the black box model. So that is, we suppose that the circuit C, we treat it as a random n-qubit unitary, and we suppose the algorithm has query access to C. And we ask, how many queries to C does this algorithm need to do substantially better than 2 over 2 to the n on this benchmark? And what we show is that you need an exponential number of queries, something like at least 2 to the n over 4, to do substantially better than the naive quantum algorithm that just samples directly from C. We also have some other results in this paper relating to other circuit families, but this is sort of the main I'm going to talk about. And there are a few reasons why this is interesting. The most obvious one being that it's a lower bound for an algorithm that's actually been implemented in a way, an actual quantum algorithm. It's also kind of interesting because it differs a lot, even in this very restricted query complexity setting, from a lot of the normal questions we tend to study in query complexity. One way it differs is that it involves these random unitary oracles, in contrast to most query complexity lower bounds, which tend to involve, say, Boolean oracles. So you query like an n-bit string and you get back bits. But here, this is sort of inherently a quantum oracle problem. Another way in which this differs a lot from existing query complexity problems is that it's not a decision problem. So most query complexity results have to do with something where the goal is to output a 0-1 answer. But here, the output is, sort of your output is some n-bit string, and you're scored in like a continuous way based on the probability associated to that n-bit string. And basically, directly as a result of these two differences, it kind of immediately requires new tools. Like, whereas we have good tools in like the polynomial method and the adversary method for lower bounding quantum query complexity, pretty much neither of them are obviously applicable here. So I'll say just a little bit about one of the tools we introduced to deal with this, and which I think is also maybe the one that's most likely to be useful elsewhere. And it has to do with state preparation oracles. So oftentimes we want to consider quantum algorithms that have access to some resource state, some state psi. And so how can we do this? Well, one way is you can just give the algorithm copies of psi. But ideally, we'd like to say, okay, well, we want the algorithm to be able to produce as many copies of psi as it wants. So let's give the algorithm a unitary U that allows it to produce copies of psi. And usually the simplest oracle we consider is what I like to call this canonical oracle. And it's canonical in the sense that if you have any unitary that lets you prepare psi, then you can also kind of simulate this unitary. And basically all it does is it swaps psi and like some fixed state that I call bot of your choice, and then it acts trivially everywhere else. But you can consider other unitary state preparation oracles. One that turns out to be very natural in this work is what I call this random state preparation oracle. So this is a unitary matrix where the first column contains psi, and what this basically says is that it gives you back psi on the all zeros input. So you feed in 0 to the n, you get psi. But everywhere else, this unitary acts randomly. Even like har randomly, let's say. So what can we say about how these two compare in power, well, what we actually show is that even though these two resources look very different, from a computational perspective, they're actually essentially equivalent in the sense that you can use one to simulate the other up to like exponential precision. So I think that's everything I wanted to say about the techniques. I'll just conclude with a few open problems. The most obvious one is to tighten our bounds. So like I said, there's this like 2 to the n over 4 lower bound, and the best upper bound we have is like 2 to the n over 3. So there's a gap which would be nice to close. It would also be nice to give more evidence that this problem is actually hard in the real world. Like I said, for the classical analog of this problem, Aronson and Gunn did something like this. They based it on a particular complexity assumption, but even their argument doesn't really seem to work for the quantum setting. So some new ideas are probably needed here. And finally, I think it would also just be interesting to explore more properties of random quantum circuits. One assumption that's sort of implicit in this work is that these random quantum circuits exhibit a sort of computational pseudo-randomness property. So they're essentially indistinguishable from the Haar measure. And I don't know if this is true, but it seems plausible, and it would be nice to be able to place this assumption on more solid footing. So giving more evidence for such a pseudo-randomness property is something I would be interested to know more about. And I think I'm about out of time, so I guess I'll end here.
Okay. Thanks. Yeah, sorry, I had my timer. Yes. Oops, I don't know how to shut it off. Okay. Well, thanks for the great talk. I think next up is Chi-Ning. So if you're here, you could start the. Okay.
Can you see my screen?
Yep.
Okay.
Okay.
Thanks, Anand. Okay, then I'll get started. Okay, so hi everyone, I'm Chi-Ning from Harvard. This is a joint work with Boaz and Xin, and on the spoofing linear cross-entropy in shallow quantum circuits. Yeah, so this is very similar to previous talks on quantum supremacy. Okay, so the motivation of quantum supremacy is about extended Church-Turing thesis, which state that all the feasible and efficient computation in the physical world is in BPP. But we also know that the seminal Schur's algorithm show that factoring actually is in BQP. Yeah, so if BQP is realizable in the physical world, then it seems that Schur's algorithm already refute the extended Church-Turing thesis. But can this really happen? Yeah, especially to demonstrate Schur's algorithm in real world, actually we need roughly about maybe 2,000 number of qubits, which is far from current technology. So in order to study whether a quantum device is really implementable in the near future, and also try to see if extended Church-Turing thesis can be refuted in the near future, we need something in the near term, in the middle, try to see if this is the case. And so here, quantum computational supremacy comes up. It is like a compromise between theory and experiment. Yeah, and the proposal of quantum computational supremacy is to demonstrate the power of quantum computations, like in maybe only like 50 to 100 number of qubits, and try to show that we can really implement a quantum computer device to do that. And the classical harness, like the classical computer cannot do that in a reasonable amount of time. And there are many proposals like random circuit sampling, boson sampling, and IQP. And today I'm going to focus on one specific candidate called the random circuit sampling, also mentioned in the previous talk, used by Google. Okay. So let me quickly describe what random circuit sampling is, and using a two-party communication game. So you can think of there are two parties. One is the challenger and one is the prover. Where the challenger is some quantum skeptics. He will pick some unitary gate for the quantum circuit, and maybe also pick an initial input gate. And then the prover, for example, Google, will try to implement this circuit and try to sample output strings according to this random circuit chosen by a challenger. And then you will send the sample back to a challenger, and the challenger want to verify whether the distribution of the samples follows the ideal distribution defined by the circuit. And intuitively, it's like without the contentness, the prover probably cannot sample the string follow the ideal distribution. So this should only work if the prover can implement the content device. But the key thing here is like how to verify. Yeah, because in order to verify the sample does follow the ideal distribution, this kind of like a chicken and egg issue, because you somehow also need to implement the content circuits to verify this. Okay, so the way Google chose to do the verification is use this something called a linear cross-entropy benchmark. So this is like a variations of what William mentioned before. And you can think of it, the linear cross-entropy benchmark, abbreviated linear XCB, as a certain statistics of the distribution P you are sampling from. So this red P is like a distribution of the prover is sampled from. So ideally, this P should be the ideal distribution Q sub C. But because there's some noise, so the distribution might not be that case. And for distribution P, we can define this value linear XCB. And due to the time limit, I won't describe too much on this, but the key point is about the two property. First is the completeness. Yeah, if the distribution P you are sampling from is the ideal distribution QC, then the value will be close to 1, which in William's setting is like 2 over 2 to the n. Yeah, here there are different normalization. And the soundness is like when the P sample from the uniform distribution, which is like you don't have any content power, then the linear XCB should be close to 0. Yeah. So the communication gain of content supremacy, you can think of it as we want to see whether the prover can generate a distribution, find a P and having large linear XCB value. And the computational hardness is like if the prover don't have content power, then the value should be like exponentially small. Good. So given this, we can quickly see what Google did. So Google chose this specific 2D linear nearest neighbor circuits, and they do qubits from 12 to 53 and depth from 14 to 20. And what they did is like they can simulate up to depth 14, and then they extrapolate real result to depth 20. And they show that from the extrapolation, they show that they can achieve a linear XCB value about like 2.24 times 10 to the minus 3. So actually, it's also far away from 1, but they claim that for classical computer, to achieve similar level of linear XCB, require 10,000 years. So this is what Google did. And we think, yeah, indeed, Google did make significant progress, but the classical hardness side is really not very solid. So specifically, the 10,000 years claim on the classical hardness is on the full simulation of the quantum circuits. But we know that actually what they really did is to fool the linear XCB task. Yeah, and also some other groups already have some empirical evidence that this estimation is highly overestimated. And the linear XCB itself also not very well studied. So in this work, we want to focus on trying to understand if linear XCB is really difficult for classical algorithms. And our answer is positive. Yeah, so specifically, sorry, due to a time limit, so I need to be faster. Yeah, we observed that a full simulation might not be necessary for achieving high linear XCB. Yeah, so specifically, we can utilize, leverage the structure of linear XCB and the circuit structure and achieve the following theorem. So this is a corollary of our general theorem. We can design an algorithm, classical algorithm, that can, like for Google's 2D circuits, if the circuit is shallow, like the depth is log n, then we can achieve in time 2 to the d squared quasi-polynomial time with linear XCB value inverse polynomial in expectation. Okay, so this is much higher than what Google can, like, because their hardness is based on exponentially small linear XCB. But the drawback here is that we can, okay, yeah, sorry, yes, I'll be quick. Okay. It's like we can only do log depth. Okay, So since I don't have too much time, so I'll be very rough on the intuition. But the intuition is to use some local information that we can leverage from by the low depthness. Specifically, if the depth is short, then the marginal of each output qubit can actually be efficiently estimated. And we can use that information to bias the sampling algorithm and achieve high linear XCD. And the intuition of the theoretical analysis is through a random walk mapping. And yeah, please go to my long talk for more details in our paper. Yeah, but to conclude, yeah, we think the Google quantum supremacy indeed is a very important breakthrough. But the classical harness is very less studied, and it is very interesting, both theoretically and empirically, to study more on this. Okay, thanks for your attention.
Thanks for a great talk. I think next up we have Nengkun, if he's here. I think so, right? Unless there's been a schedule change. Okay, maybe he's not here.
He's typing in chat.
Oh. On GatherTown or?
In the Q&A.
Oh, okay. Oh, it says he is here.
I think he's an attendee instead of a panelist.
Okay. Maybe there's a way I can promote him. Promote to panelists. Okay, great.
And I think you can promote.
Oh yeah, thanks.
Oh, okay.
I think he's now a panelist. Do you want to try? Hello.
I'm here. Hi, Anna.
Hi. Yeah. So do you want to try sharing your screen?
Sure, sure. Let me see. Share screen. Yes.
Okay, great.
Sorry.
Oh, no problem.
Sorry.
So I guess I'll do the introduction. So next talk is sample efficient identity testing and independence testing of quantum states by Nengkun Yu.
Oh, thanks, Anna. So I'm Nengkun Yu from ITCS. Thanks for attending my talk. So property testing was studying this problem. For X in S, we want to decide whether X in a subset of SP by local queries. And for distribution testing, which study that given samples or observations from one or more unknown probability distributions, we want to decide whether it satisfies a certain model. And for property testing, usually we want to study distributions. We want to say that whether for X in S, we want to decide whether X in P or X is outside Q with high probability. And distribution testing, many important problems has been extensively studied by TCS community. For instance, the identity testing, independence testing, and conditional independence testing. Well, many smart ideas and techniques based on the L2 norm analysis. For quantum property testing, we are focusing on this problem. Given copies from one or more unknown quantum states, we want to decide whether it satisfies a certain property. This problem was initialized by Holevo at 1970s. Different from classical property testing, a great variety of measurement we need to consider. So for the joint measurement setting, we are given n copies of d-dimensional quantum state rho and a property P. We want to design a giant measurement M, applying on n copies of rho simultaneously and output a delta. Well, delta characterizes that whether rho is in P or outside P with high probability. For independent measurement setting, sorry, we want to design measurement, applying on each copies of rho and gathering out classical output together to a classical computer C and compute delta. So comparing these two methods, joint measurement might have low complexity, and but the implementation is very hard even in the future because the dimension we need to consider is like d to the k. K is the number of copies, and for many questions, k has to be poly d. And quantum property testing has been widely studied. For instance, the tomography problem output a good estimation of a given state. Spectrum testing output a good estimation of the spectrum of a given state. Identity testing and shadow tomography online learning. But you can see there's a gap between classical property testing and quantum property testing. Classical property testing only have one sampling method, which is called counting. But quantumly, usually we're using Chou duality to achieve small sample complexity. Therefore, many smart ideas and techniques of classical property testing are not used in quantum property testing. In this work, we describe an independent measurement which preserves the L2 norm of quantum state. So the formal statement is as follows. For d-dimensional quantum system, there's a deterministic, there's a measurement M such that the output resulting probability distribution P and Q for any two quantum state rho and sigma satisfies this equation that the two norm between P and Q equals the two norm between rho and sigma divided d plus 1. At the same time, the two norm of P and two norm of Q is no more than square 2 divided d plus 1. Now we can have this framework to solve the general quantum property testing problem. For quantum property testing problem of L1 norm, we first apply our measurement to transfer it into the property testing problem of classical distributions. And then we call the classical algorithm for L2 norm and use the relation back to a quantum algorithm for L2 norm, and then applying the relation between L2 norm and L1 norm, we solve our original problem. So using this method, we have solved many problems. So in this talk, I'll focus on the identity testing using independent measurement and the joint measurement lower bound for independent testing. So for identity testing, we want to distinguish rho equals to sigma and the one norm distance between rho and sigma is greater than epsilon. We can use independent measurement to solve this problem using d squared divided epsilon squared copies. It's very simple because after applying our measurement, we have this probability distribution P and Q, which satisfies the equation on the right-hand side. And then we just call the result of CDVV, which show that OB divided epsilon square copies of P and Q can solve the problem that can distinguish P equals Q and the two norm between P and Q is greater than epsilon. If B is the maximum of the two norm between two norm of P and two norm of Q. So just plug in is all right. And for independence testing problem, we're working on a multi-party quantum state. So says rho 1, 2 is called independent if rho 1, 2 is rho 1 tensor rho 2. And our goal is to distinguish whether rho 1, 2 is rho 1 tensor rho 2 or rho 1, 2, the difference between rho 1, 2 and any sigma 1 tensor sigma 2 is greater than epsilon for any quantum state sigma 1 and sigma 2. We actually only need to distinguish rho 1 case that rho 1, 2 equals to rho 1 tensor rho 2 from the case that rho 1, 2 minus rho 1 tensor rho 2 is greater than epsilon divided 3. So because we only care about the latter case. And the problem is simple because we can call identity testing in the sense that for a given copy of rho 1, 2, we can generate rho 1 by tracing out rho 2. And we can also, another copy of rho 1, 2, we can generate rho 2 by tracing out rho 1. So then we only need to verify whether rho 1, 2 equals to rho 1 tensor rho 2 or far from each other. And similar ideas for identity testing of collections and independence of collections and conditional independence testing of quantum classical quantum state. Now we want to show the lower bound for joint measurement for the problem of independence testing. So one can our result is that on a signal
1 minute, by the way.
Pardon me, 1 minute. Okay, thanks. So we want to show that D1 tensor D2 divided epsilon square copies are needed for the independent testing in D1 and D2 system. So if D1 and D2 are very large, we can just employ the independence testing to test whether rho 1, 2 equals to I1 divided D1 times I2 divided D2. By first test whether rho 1 is I1 divided D1, and then test whether rho 2 is I2 divided D2. Then test the independence of rho 1, 2. And we only need to recall that result by O'Donnell and John Wright says that 0.15 D divided epsilon square copies are necessary to distinguish whether rho is maximum mixed. But this method does not work for large D1 and small D2 because step 1 here already use the same order as the maximum mix testing. Our method is using dimension splitting. So we just split general 2 by D system into log D qubit system. And then we test whether each qubit is a maximum mix. And then we test whether rho is independent through the 1 versus log D cut. And the main technique is here, though, we want to, is M+1 qubit state is epsilon close to be independent from any 1 versus M partition, then it is 5M epsilon close to be M+1 partied independent. And then we solve the problem. Thank you very much.
Okay, thanks. Thanks for another great talk. And the last talk is by Uma. So I guess, Nengkun, if you want to stop your screen share.
Sure,
then...
sure, sorry. So stop sharing. Sorry. Maybe I'll just leave.
Okay, looks good. So yes, I guess the last talk will be by Uma Girish on quantum versus randomized communication complexity with efficient players.
Thanks, Anand. This is based on the joint work with Ranraz and Avishay et al. The setting is communication complexity. So there's a function that takes as input 2 binary strings and it outputs a bit. Alice gets one of the strings and Bob gets the other string, and their goal is to compute this function. And they want to do so while minimizing the amount of communication between them. Note that a trivial protocol is to have Alice send her entire input to Bob. This costs n bits of communication. So we are interested in small cost protocols, that is protocols that do much better than this, protocols that have cost polylogarithmic in the input size. In this talk, we'll be interested in partial functions, that is functions that are defined on a subset of points, and Alice and Bob only need to solve this function on that subset of points. This is the general setting of communication complexity. We're interested in the following 2 models. The first is the classical randomized model, where Alice and Bob share public coins, and their goal is to compute the function with high probability while minimizing the worst case number of bits that they exchange. In the quantum setting, there are 2 differences. The first is that Alice and Bob share EPR pairs. The second is that they can exchange qubits. As before, their goal is to compute this function with high probability while minimizing the number of qubits that they exchange. We're also interested in the number of rounds. In 2-way communication, Alice and Bob can interact with each other. In 1-way communication, Alice sends a message to Bob, and Bob has to decide whether the function is 0 or 1. In simultaneous communication, Alice and Bob don't talk to each other. Instead, there is a third party, Charlie, a referee, to whom Alice and Bob send messages. Charlie, upon receiving the messages, has to decide whether the function is 0 or 1. These are successively weaker models. That is, there are functions that are easy in 2-way communication, but hard for 1-way communication. Similarly, functions that are easy in the 1-way model, but hard in the simultaneous model. The main problem of interest is this. Is there a communication problem that has a small cost quantum protocol, but no small cost classical protocol? Is there a function that's easy to communicate when you can exchange qubits, but exponentially harder when you can only exchange classical bits? Does quantum provide advantage in the world of communication complexity? For total functions, this is a major open question. We don't know the answer to this. For partial functions, on the other hand, there is a long line of research spanning over 20 years, all of which demonstrates in various ways that quantum communication can provide advantages. The first such result was shown by Burman, Cleve, and Wigderson. They show that in the 0-error setting, when you want to answer correctly with probability 1, there are functions that are easy in the quantum simultaneous model, but hard in the classical 2-way model. So this is saying that a rather weak model of quantum communication can exponentially outperform a rather strong model of classical communication. In the bounded error setting, when you want to answer correctly with high probability, the first such result was shown between quantum 2-way and randomized 2-way. This was strengthened in various ways, and the state-of-the-art result is this, which is that quantum simultaneous when Alice and Bob share entanglement can exponentially outperform randomized 2A. So let us state this result more formally. This is due to Gawinski. This is the state-of-the-art result, and it essentially subsumes most of the previous bounded error separations. So Gawinski demonstrates a partial function which has a small cost protocol in the quantum simultaneous model when Alice and Bob share a few EPR pairs. However, there is no randomized protocol of small cost regardless of the number of rounds. This is the state-of-the-art result. Now, one drawback of this result in the context of our work is that this protocol is not efficient. So what do we mean by an efficient protocol? So we say that a quantum protocol is efficient if it can be implemented by a quantum circuit of small size with oracle access to the inputs. So roughly speaking, this means two things. The first is that everything that Alice, Bob, and Charlie do can be implemented by quantum circuits of small size. In other words, the amount of work they do to prepare and process their messages is not too large compared to the size of the messages that they're sending. The second is that the oracle access to the input, it just means that Alice, Bob don't need to read their inputs bit by bit. Instead, they can make a few queries to their input in superposition and still be able to execute the protocol. The quantum protocol in this theorem is not efficient because Charlie, the referee, needs to perform n many measurements one after the other. And this seems to be really crucial for the lower bound to hold. So we ask this question, is there a separation where the quantum protocol is efficient? Our work addresses this. So we show that there is a partial function which has an efficient small cost quantum simultaneous protocol when Alice and Bob share a few EPR pairs. However, there is no randomized protocol of small cost regardless of the number of rounds. So in other words, we qualitatively recover Gawinski separation between quantum simultaneous and two-way randomized. Furthermore, everything that the players do in our quantum protocol can be implemented by small circuits with oracle access to the input. So this is our result. Let me briefly talk about what was known about efficient separations. To the best of our knowledge, efficiency has not been explicitly addressed in the world of quantum versus classical separations. In fact, in most of the previous separations that I mentioned, the quantum parties are inefficient. Nevertheless, there was an efficient separation known between quantum two-way and randomized two-way. So this follows by applying query to communication lifting theorems to existing efficient query complexity separations. Our work kind of unites these two aspects of quantum classical separations. So one, we show a separation between the state-of-the-art separation, which is between quantum simultaneous and randomized two-way. Secondly, all the parties in our quantum protocol are efficient. Another aspect of our work is that we provide a new lower bound technique for randomized communication complexity based on Fourier analytic techniques from these two works. So the first is the polarizing random walks result of Chattopadhyay et al. The second is the oracle separation of BQP and PH due to Ras and Tal. In the remaining time, let me just describe the function for which our separation holds. So without going into too many details, let me say that our function is based on the correlation function, which was first introduced by Aronson, who showed that estimating the correlation is easy with quantum queries, but hard with randomized queries. So we take a variant of this correlation function and lift it to the communication world using XOR as the gadget. So this is the correlation communication problem where Alice and Bob want to find out whether the XOR of their inputs has high correlation or low correlation. Our main theorem is that this function has an efficient protocol in the quantum simultaneous model, whereas there is no small cost protocol in the classical randomized model.
So 1 minute.
Oh, okay, thanks. Yeah, so just to say a little bit about the proof technique, we make use of the correlation distribution as defined in the oracle separation result of PQP and PH due to Ras and Tal. So we first rephrase our problem in their framework. Now, doing so allows us to use their machinery, which says that it reduces the task of proving this lower bound to proving a upper bound on the level 2 Fourier mass of a certain function. So that's the second part of that's the technical heart of our work. We show that the level 2 Fourier mass of a function associated with a small cost protocol is bounded. So this is all I want to say about the proof technique. I guess I finished a little early. So let me just show you the open questions here and finish.
Okay, well, thanks for the talk, and thanks to all the speakers for speaking this session. So now we have some time for Q&A and for general panel discussion. So if you have a question for any of the speakers or something that you want to address to all the speakers, feel free to unmute yourself and ask, or you can type in the chat or the Q&A if you prefer.
I had a question for the first speaker. So you said something about, I think this was Lior. You said something about, I might have misunderstood, but it was something along the lines of like, since the thermal state is like locally decodable or like simply decodable to like a quantum error correcting code state by like something like Spielman, you said then like the thermal state must have been like, was it entangled or something like that? And I was wondering if you could elaborate on that a bit, since I don't quite follow the logic there.
Yeah, sure. So this is kind of like just composing the depth of the circuit. So if you have a quantum error correcting code, then any code state, even like the uniformly mixed state over all code states, is highly entangled in a well-defined way. Because you can just show kind of by light cone arguments that you need like logarithmic depth. Now, specifically for inverse temperature, which is 1 over log n, so the Hamiltonian construct there, then you can show that the errors form clusters which are at most, say, logarithmic. So if you apply Sifter speed on decoding, you can kind of completely annihilate the error in depth, which is log n. And so, in other words, it means that like if you reverse the depth, well, it means that you could have generated the thermal state by applying a log n depth circuit over a log n depth channel, which means that overall the circuit depth is retained. So this is the kind of argument that is used there.
Okay, I think I follow. Thank you.
So by the way, Lior, it looks like there's a question in the Q&A from Anurag about whether the log n temperature is due to the current QLTC parameters.
I'm sorry, I couldn't hear it.
Oh, I think the question is whether the log n temperature in your result does that follow from like the current best known parameters on QLTCs?
Oh yeah. This is kind of like it depends on the topology. So right, like this is kind of like a clash between two forces. You need on one hand good quantum locally testable code, and on the other hand, you want the topology to be such that if you examine, like zoom into the small segment of qubit, it has a good bipartite expansion in terms of qubits to constraints. Now, the point is that the construction only allows for this to hold for log n size 10. If you can push this higher to, spanning over linear sets, then you would be in a much better shape if you push up the temperature. I think it's a matter of finding the right topology, right? So it's hard, like even classically, to have something which is both Tanner graph bipartite expander and quantum locally testable. So yeah, this is like an open question which I think progress can make.
I see. Thanks. Maybe I can ask a question to, I think, mainly Chi-Ning, but also William might have thoughts on this. I guess, so your result shows that for circuits of fairly short depth, you can like spoof this this cross-entropy benchmark quite a bit shorter than the actual depth of the Google circuits, at least. It's like, do you have like any thoughts on like what like the depth threshold might be where things start getting hard to spoof?
Yeah, thanks for the question. So yeah, so if we are using exactly the same algorithm, then indeed there will be a limit. But actually, in the follow-up work, we are actually trying to design other variants of the algorithm using similar ideas. like creating some defects in the circuits, etc. And we are able to handle much larger depth circuits. But the theoretical analysis is much more difficult. Yeah. So for that follow-up, we are mainly working on empirical simulation to try to really see what linear XCB we can achieve. And for now, it's hard to say. Like, it's actually very delicate. Yeah, like the algorithm still can achieve non-trivial linear XCB using similar ideas, but it's unclear what's the scaling. Yeah, because as I said, like the Google, this kind of verification is very expensive. So it's actually very difficult to do simulation. So we actually need to use Google Cloud to try to study Google supremacy.
I see.
Yeah.
I mean, wasn't there a recent result? I think it was by Fernando Brandauer and some other people showing that like a certain level of depth is needed, even just for to guarantee that quantum circuits anti-concentrate, and that's basically the assumption you need to get that the linear cross-entropy output probabilities are distributed nicely. So I guess I would guess the depth would need to be at least that.
That's only log n, so it's
right.
Order.
Yeah.
I don't remember what the constant is, but yeah.
But I also wouldn't be surprised if it needs to be much larger than log n.
I see. And I guess the Google depth, by the way, is like square root n, if I'm remembering correctly. Is that?
Yes. Yes.
Okay.
I mean, it's so hard to say because it's all constant, but I guess,
right.
yeah. I mean,
they want you to think
n is 53 and depth was like 20, I believe. So.
Right.
And I think also intuitively, like the XCB achieved by Google is also actually exponential. It's like maybe 2 to the minus CN, SCD exponential in depth for some constant C. And our algorithm also roughly maybe 2 to the minus C prime D. So in the end, it's really comparing the constant in the exponents, and then it's not very clear, like because for different circuits architectures and even different ensembles have different constants. So.
And like, is the exponential in their result? That's just from like the constant error rate per gate or something. You'd expect it to. Okay. See, so that does sound very delicate.
The noise. Yes.
Yeah.
I had a question for Uma. I was wondering if you could say some words about like you mentioned that you're like part of your technical work is like this bound on the Fourier mass of the second level of some functions. So I was wondering like if you could maybe state this, like what the bound you're able to achieve is, and like on what type of functions it applies.
Sure. So let's say the protocol is C of xy, where x is Alice's input and y is Bob's input, and C is the output of the protocol. So so we consider the following function, which is expectation of C of xy, where x XOR y equals z. So take a random pair of inputs x, y for Alice and Bob, conditioned on their XOR being equal to z, and look at the expected value of the protocol. So then look at the expected output when the inputs are sampled according to this distribution. So this is a function of x XOR y, and we bound the level 2 mass of Fourier mass of this function by the cost of the protocol. So by level 2 Fourier mass, I mean sum of mod of f hat s, where s is of size 2. So sum of mod of level 2 Fourier coefficients is at most the cost of the protocol. So so actually we bound this by cost square, and this is why we get then to the 1/4 bound, lower bound. So.
Okay, so and then the pass from like the second level Fourier mass upper bound to, or rather the lower bound of the cost to, like this thing is like just is other stuff that's probably hard to explain right now.
It's hard to describe shortly, but this is kind of the bulk of the work of Oracle separation result and things like that.
I see. Thank you.
Sure.
Oh wait, sorry. One quick thing. So like, if you were to, if you're able to get like upper bound of cost, then would you get like
Exactly.
into the one? Would you be able to get redone?
Exactly. Yep.
Okay.
I also have a question for Uma. So one of the main contributions of your work is this: the players in this exponential separation, like the ones that have the smaller complexity, are actually efficient. That their complexity, if you view the input at least as a query input, is of similar complexity, similar to the amount of communication, log versus poly or poly versus exponential. Has this notion of, and you also mentioned this notion of efficient players hasn't been considered before in the quantum context, like the quantum versus randomness question. Are there other contexts where people study this question? Like, for example, in just like, I don't know, randomized versus deterministic, has this been studied?
Probably only in the context of interactive proofs, I remember it, but probably not in separations, as far as I remember. When you have things like equality, which kind of demonstrate this, so I guess it's efficient in the randomized world, but hard in the classical world, deterministic world. So.
Oh, I see. Is the protocol for equality also efficient for randomized players?
I guess, right? These hash functions.
Actually, I think it might not be, because don't you have to query the whole?
Yeah.
The way I think about it is you inner product it with a random string. But
yeah, so that's inefficient. Yeah. So yeah, that's a good question. I don't think it's been explicitly addressed in separating models. The only context I've seen it is in interactive proofs and things like that.
Great. Thanks.
I maybe have a question for Lior, but also the next session is about to start. So those who want to switch over should feel free to do that. But my question for Lior is just, I remember there's, so your theorem statement has these two conditions, right? That there's like, you want the Hamiltonian to have topological order for the ground state. And then you say you also have like circuit complexity and on like mixed states, but like, I mean, there's some discussion of like, you could take the Hamiltonian for a classical code and look at the Gibbs state of that. And like, that might already have like high circuit complexity. So
right. So
yeah.
So yeah, the conjecture is kind of stated to rule this out, right? So if you have like, so let's just say this, right? So if you have a classical LTC with large like linear distance, right? So the third such code, then yeah, it's hard to sample from the distribution. So you need like log n circuit complexity. But so then the first condition of the conjecture calls for you to have some quantum entanglement, actual quantum entanglement at zero temperature, and that you cannot achieve with a classical LTC. So the idea is, right, so you start off with a quantum, like the idea is you start with a quantum state which is entangled, then you let it thermalize, and then you come back and check on your state and see if it's still entangled after a long while. Mm-hmm. And if you succeed in that experiment, maybe like you have the right Hamiltonian.
I see.
Does that answer your question?
Yeah, I think so. Yeah, at least that, it's just clear why I like this picture of like you start in the ground state and let it thermalize. Like that makes it see like a nice.
Yeah, I mean this is like this is what the thermal state does.
Right.
Which is some form of equilibrium, then you can ask whether it's now it's entangled or not.
Yeah. Well, I don't know. Are there any other questions, or should we close the session and move to the next room? I guess not. So, well, round of applause for all the speakers, and